So you want to go ahead and look at your drawing, go through all of that. Is it tight? Is it dipping? Is it tilted like you're recumbent or upright? Is it cylindrical? Is it non-cylindrical? Go ahead and string it together, and then you can come up with a name for your fold, like a cylindrical, plunging, tight fold, or a recumbent, upright, gentle fold, things like that. So go ahead and don't worry so much about which order, although if you're unsure, you can just go in the order from that slide where I had them numbered 1 through 4. Just start at the top, go with 1, 2, 3, 4 for the parts of your fold. Keeping in mind that one of the parts has 2 things in its name, because you're looking at the plunge and the tilt of whether it's recumbent, intermediate, or upright. Now, in the profile of a fold, so now we've cut straight across it. We're not looking 3D. We're just looking 2-dimensionally at that side view straight across the fold. We can connect points on the inside and the outside of the fold that used to be directly above each other. So think of it as like you have a layer of rock that's nice and flat and horizontal, and you go in there and you paint stripes. Then over some extended period of time, it gets folded, and you come back and you look to see what the stripes look like. Now, there's 3 different ways that these lines or stripes that aren't really there, but we can figure out based on the rock and the crystalline structure and cracks and other things like that. We can see they can be convergent, parallel, or divergent. I'll show you what I mean. These are all convergent because the lines are closer together on the inside of the fold than they are on the outside of the fold. You notice here, here they're extremely closer together. Here they're mildly close together. This one has a sub-description of parallel, but it's still part of the convergent, not the overall parallel. So this is Class 1A, Class 1B, and Class 1C. All Class 1 meaning convergent. You can see here the angle is changing. Here the angle is not changing much. And here the angle is diminishing as it gets towards the top. Parallel is like this. Parallel is less common. If you look at these convergent ones, this is what you might think of. If you take something, like if you take a big chunk of Play-Doh and you hold it in your hands and you bend it, the outside of that arc is stretching, so the lines are spreading apart. The inside of it is getting squished, the lines are getting closer together. It's kind of a classic fold type. The parallel Class 2 is a lot more caused by shearing. Think of like you have a deck of playing cards. All the cards are parallel to each other in a nice stack. And you hold it and you use a finger and push on the middle of one of the sides. You get this arch shape, but the cards are all still parallel to each other. So you get a fold where everything is still parallel. Also called a similar fold. A divergent, again, remember that we're talking about how the lines go from the outside of the fold to the inside of the fold. And here, they're closer on the outside, and they diverge from each other as they get to the inside of the fold. So this is a divergent class 3, and this can happen when you have shearing and compression. So you've got compression from the sides, and you have shearing in the middle, and you can end up with this divergent type fold. Now, the next section looks at fold systems. So now we're not looking at just one fold, we're looking at a bunch of folds. And what can you see in the folds as a group? Are they symmetric? Are they asymmetric? So for a symmetric, we've got axial surfaces that are parallel and perpendicular to the enveloping surface. The enveloping surface is if you connect all of the peaks or connect all of the troughs. Asymmetric, you've got not 90 degrees anymore. So they may be parallel to each other, they may not be parallel to each other, your hinge axes, or axial surfaces rather, but most importantly, they're not perpendicular to that enveloping surface. So example A is symmetric, example B is asymmetric. Parasitic folds are when you have little folds within the big fold. So the big fold, shown by the dotted line, also is an enveloping surface for these little folds. And because the little folds got folded in this big fold, we have asymmetric and symmetric folds in different parts of the system. Over on the left, we have asymmetric. Their axial surface is not perpendicular to that enveloping surface. And it's a Z-type clockwise asymmetric fold. If you look at it, kind of tilt your head to the left a little bit, you can see it almost looks like a series of letter Z's. So, and it's tilted clockwise. So that's why it's called a clockwise or a Z fold. At the top, they're symmetric. They are perpendicular to that enveloping surface right near the peak of the big fold, and also called an M fold. If you look at it right where my mouse is, it looks like a letter M. On the right hand side, if you tilt your head to the right a little bit, you can kind of see the shape of the letter S. And you can see that the axial surfaces are not perpendicular to the enveloping surface. They are tilted left or counterclockwise. So these are called counterclockwise or S folds. Here again you can see we have M folds, perpendicular. These are symmetric. M folds are always symmetric. Here we have some Z folds at the top and some S folds on the bottom, also known as clockwise on the top and counterclockwise on the bottom. Now, on the left here, we have Z folds, M folds, and S folds in the proper orientation. This happens. On the right is what happens if you get it backwards and switch your S folds and Z folds on the wrong sides. First of all, you don't get an M fold at the top. Second of all, you do get a Christmas tree shape, and this doesn't happen. We have no Christmas trees underground out in the world. Christmas trees like to grow on the surface, so never draw a Christmas tree in your folds in the ground. Now, sometimes we have strange special folds. We can have a monocline. Only one limb is tilted. You can see right here, the left-hand limb is tilted, and to the right, there's no tilt. The layers are nice and horizontal, like we'd expect them to be right after they were deposited. So this is a monocline. Kink folds are very small. You can see here is a little hand compass for scale. Small folds with straight or nearly straight limbs and very sharp hinges. So they're tight, sharp folds with straight limbs. Some of these limbs in this picture are straight, some of them are less straight, but the kink folds are the ones where it's a sharp fold with straight limbs. Chevron folds are large scale. So the kink folds are small. Chevron folds are basically a large scale kink fold with straight limbs and sharp folds. Generally, these will have nicer, straighter limbs and nicer, sharper folds. And if you have any military background or family in the military, Army and Air Force especially, you're probably familiar with chevrons. Chevrons are on all the enlisted people's shoulders for their rank. Same kind of shape, that sharp angle with straight lines in a chevron fold. Box folds are where some of the limbs are nearly parallel and squished inside, are kind of like M or W shapes. So you can see here the box fold on the left and right are nearly vertical limbs, and in the middle it's squished, kind of a big M. Tigmatic. The P is silent, so tigmatic. Tigmatic folds are irregular, they're isolated, tightly folded, and thin layered. So 4 things that make it a tigmatic fold. So they're thinner than everything else nearby. They're isolated, so it's pretty much the only layer like that nearby. Nearby being a relative term. They're irregular, so you can see this white tigmatic layer that's folded. Each little bend in it is different than the ones next to it. Very irregular. It's isolated. It's in this big mass of gray rock. Tightly folded. Most of these folds are very tight. And it's thin. It's a thin layer relative to all this dark gray rock around it. Doubly plunging folds. Remember this, doubly plunging folds. This is going to come up on labs. We talked about folds that plunge in one direction. Well, sometimes, if they're folded in the middle, they can plunge in 2 directions. So, we can see this antiform here, eroded and exposed, but it plunges also towards the top of the page, and it plunges towards the bottom of the page. It's dipping down into the ground at both ends.